All right, welcome back. In this video, we're going to continue our discussion on flexural members, but we're going to kind of stray into a new topic involving flange sections. Now, flange sections have important uses in construction. They're very useful in the precast industry, and there's some issues that we haven't yet addressed in our study of the singly reinforced or the doubly reinforced sections that do arise here. Now, the analysis procedure that you'll see is very, very similar to that of the doubly reinforced sections, and with a little bit of a twist, it does seem pretty logical in its approach. So now, basically, what we're looking at is typically reinforced concrete beams are integral with a concrete slab. Okay, basically, what happens if you look at I've got kind of a simple cross section here is that this would be considered, simply supported between the columns, or it could be continuous. It doesn't really matter. But normally we like it so that I can take advantage of the width of the flange section being greater than what you would have on a rectangular section as far as the compression block of the concrete. So if I can take advantage of that, then I can get some increased capacities for smaller section sizes or amounts of steel that are present. Okay. Flange beams can come from a number of ways. It can be, a primary member, like I said, that goes from column to column, in which it's a slab that's built integral with, with the girder. And this is what we would probably call as a one-way slab, in which the bending moment of the slab is this direction. Now, you could design the slab itself as a rectangular beam, but the guy that's holding him up, could be the supporting condition. And so obviously there would be some load that causes a positive moment here, and a negative moment maybe over the support if it's continuous. And so we need to take that into account as well. Another way that it can be built, or that you can have this kind of scenario set up, is that maybe I have just a regular rectangular beam, or I guess technically it could be a T-beam too, and then the secondary members are framing in flush to the side of this, okay? And again, the slab is forming part of that extra with the flange. A lot of times we don't necessarily build a beam with a flange on its own. It's generally because it's being built integral with some sort of floor system, and I want to take advantage of the thickness of the slab to kind of help us with the load carrying capabilities. All right. Okay, now, there are a couple of different types of flange sections that we're going to be looking at. Okay, and one is what we call as an L-beam. Now, if you look at this upside down, it does look like a shaped L, but this is a one-sided flange, meaning that it's a rectangular section, and then I have a flange off to one side. And this occurs a lot, as you can see kind of in those previous photos, whenever you have a girder that's at the edge of a building, in which then on the face of the building would be here, and then this would wrap all the way around the structure. I would have this one-sided phenomenon. And then more often the T-beam, which is our other one, in which I have flanges on both sides. Now, the flange doesn't have to be equal width on this, and we'll show you why that is with some assumptions and some ACI requirements here in a little bit. But you can see that those are more like interior spans, so that this slab were to continue on, and maybe there's another one, so forth and so on. So one-sided and two-sided are treated a little bit differently. It's the same approach, it's the same table that we're going to reference, but this is kind of the pictorial of what's happening. Now, the analysis that we're doing here is all going to be singly reinforced. A singly reinforced section in which I only have steel in the tensile region, which would be at the bottom. So this also kind of puts us into, we're analyzing simply supported beams or beams where, my tensile steel is at the bottom of the section. Because what happens is if this section goes into some sort of reverse bending in which I get a negative moment, at the top, in the section, then my tensile steel would need to move up to the top. Well, now all that steel moves into the flange region, okay? And more often than not, this is, we have to kind of watch out for, what happens with, rectangular sections when I decrease the area. I can overload in compression some of the other sides, some of the other the narrower flange of the two. So that's our classic definition of a flange section, or a T-beam, if you will. Okay. Now there is one other application that we kind of hinted at a couple seconds ago. Myself situated here. And that has to do with a third kind of flange section, which isn't the most efficient, but it's kind of what we described with the case where I had a T-beam that had a negative moment on it. Sometimes we have what we call an inverted T-beam. in which I put an amount of tensile reinforcement here, and then my compression block is this zone that's in what would be the stem of the beam. Now these are really, really handy in the precast industry, because what I can do is I can build this piece, to connect between two columns, and then all of a sudden I have a ready-made shelf for a precast element to just sit in on. And so this, these can be very, very quick in construction. And are often used in structures like parking garages. If you go take a look at one of those, they almost always have an inverted T-beam running between the columns, and then whatever section, the double T's or whatever that they're using in the parking garage it'll just bear right here, and you can have a metal plate or some sort of neoprene pad or something that helps with the stresses. Now there is some design considerations that we're not going to address in this, in which I would more than likely develop tension at that corner, which means that I would have to have some sort of reinforcement across here to kind of help produce this haunch or this core bowl landing happening here. But it is these are pretty common in practice. Now maybe not so much in the in the RC field, but definitely in precast or pre-stressed applications. They're very, very useful for those. Okay, all right. Now, if you look, this is kind of what we're describing about these moment reversals. If you kind of look at the crack patterns, I'm assuming I have load that's acting, down along the length here, that I would get, in the middle of the region, I would get cracking in the middle, which means reinforcing needs to be at the bottom. And then coming over the supports, these continuous effects, I would get cracking in the top, which means I would need the steel in the top. And so the way that we analyze these will be a little bit differently. Now, we haven't even talked about slab reinforcing yet and the requirements for that. And so we'll want to, sometimes we can incorporate the reinforcing in the slab as being part of the reinforcing in the beam. But in this exercise, we're just going to look at how do I analyze this for capacity, for our capacity cases, right? So I've got a couple of pictures here. And so what happens is, if I correlate back to our picture, I've got section A. This would be our reinforcing with the primary, AS amount here being located at the bottom, and then a couple of bars at the top for, whether it's just to help hold up the stirrups or if it's actually being used for capacity, this would be some sort of AS prime happening here. And then when I look at section B, which is now the one over at the support, it flips. This now becomes AS, and this guy becomes AS prime. Okay, and so you would have to come up with reinforcing patterns that will solve both of those problems for both the maximum positive moment and the maximum negative moment. Okay, so that's why we need these envelopes, and we've got to be able to know, what the largest of the two is for beam. And this is a major, major issue in continuous structures. And so I want to take care of that. Now, one of the issues that we have with all of this, okay, has to do with the effective flange width. And that the idea being that what I've drawn here is a little bit of a multi-span kind of structure, and maybe I have another rectangular section over here and then another one that goes off the page as well. But what happens is if these are, the question becomes, and we have to compute what we call the effective flange width. If these two are very, very far apart on there, it would seem logical. One of the things that we could do is just, let's locate the center line of the open span, and we'll just give half of it to either side. Now, if these are very, very close together, then that's a pretty reasonable estimate, depending on what these effective dimensions are for the one-sided and the two-sided. But if I start spreading these things out so that it gets a lot further apart, now there's a region out in the middle that may or may not be doing its share of the work. And so we have to come up with, what we call this effective width for the flexural capacity of these flange sections. And that's the challenge of this. All right, and so ACI in their section 6.3.2 here gives you basically the prescriptions for how do you compute BE. So even though maybe the whole width is, maybe it's 10 feet to the center line, I may only be able to count 6 feet of it as being effective in helping this section resist the moment. Okay, and but it all kind of keys off of figuring out where the center line of the span is. And so we're going to take, the half of the clear span, okay, which that's one of the requirements that they're going to have. And this clear span is from inside face to inside face of the beam. In fact, you can see that on this other picture that I have drawn down a little bit further below. Okay, so if I draw my T-beam or my L-beam and I draw my T-beam, this SU dimension, which is the transverse span dimension, is going to be from the inside face to the inside face. And then the width of the stem, that's what we're calling is BW. And then on the other side of this guy, I would have another S, a clear span dimension. And like I say, they don't have to be equal. Sometimes they are, sometimes they aren't. But, the effective flange width that we're going to have is going to be based off of these dimensions that we'll try to set forth. So we have the transverse span, which is between him and his neighbor girder or beam. Okay, and then we have the measured length of the beam itself, which is the main span, which would be down the length of the beam. So you got to make sure that your S's and your L's oriented correctly. Okay, the other variable in all this is the thickness of the slab, which is what we're going to call as HF. Okay, and you can kind of see that on these pictures. All right, so all of the effective flange width calculations come out of this table 6.3.2.1, and I apologize, it's a little blurry, but you can kind of see it as it's pretty easy to see the way it says. So if I have flange location on each side of the web, that's our T-beam. Okay, and for the one side of the web then would be our L's, and it could be that guy or it could be this guy. It doesn't matter which way as far as coming up with the provisions. And ACI in this table prescribes some of the dimensional limits that you have to check, and it's the smaller of each of the three of these. Now, just so we can see it, I've rewritten these on the next page so you can kind of see. All right, so for the one-sided case, which again, that's our, that was our L case on here. The effective flange width, which is this dimension that you're allowed to count on, okay, is the smaller of BW plus 6 times the slab thickness, where this is HF. Okay, it's BW plus 1/2 of SU, and you check this for both sides, or for this is the one-sided, so you check it for the side that involves the SU, and then also BW plus 1/12 of LU. So I've got a transverse span and I've got the longitudinal span of this, okay, on this. So you got to keep track of our S's and our L's on this. Again, these are all coming out of that table that I showed you at 6.3.2.1. Okay. For two-sided T-beams, okay, where I have now that guy, okay, we're going to take the effective flange width again as being BW plus 16 HF. Okay, and now if you look at the second one, BW plus 1/2 of the transverse span on one side plus 1/2 on the transverse of the other. So basically you're doing the center line to center line calculation. That's what this check is doing. So you can see it's a little bit different than the one we had on the one-sided. Here I only had the SU for the side that had the transverse span, but now I'm doing it for both sides of it if we go back to that picture. Okay, and then also BW plus 1/4 of the span of the main span, the LU for that. Okay, all right, now there is a special provision, okay, because as you saw in the pictures that we showed you before, back on that first page, is that a lot of times T-beams are built as integral as part of systems, right, in which the flexural capacity of this guy is tied to the slab, which is tied to the next guy over here. And so all three of these guys kind of work a little bit together in their behavior, okay? So what happens is that we've got to take into account, well, what happens if I only have one by himself, that I don't have these other two sides? Because what the slab does, think about a positive moment. I'm getting a compressive force in the top of this beam that's wanting to push on it. And if I push on it hard enough, then our basic mechanics says that I could buckle this guy. Okay, and if you remember from steel design, it's kind of like a lateral torsional buckling kind of effect where the top of this beam tries to kick out. Okay, but the slab helps stabilize that. If I go to a scenario where I only have one beam, I lose that lateral restraint. And so we've got to be kind of mindful of our values there. So this is what we call for a non-integral or an isolated T-beam. Okay, and so for T-beams that are isolated or single beams, not part of a force system, okay, in which the compression zone is in a flange, okay, we're limited to some particular dimensions. The first one is that the maximum effective width of this is limited to 4 times BW, okay, where BW is the width of the stem. Okay, in addition, they put a restriction on the thickness of the slab. They don't want this guy getting too thin because then he does become susceptible to buckling out of the plane, okay, or experiencing some sort of local buckling phenomenon, in which the minimum thickness of the top of this T-beam is 1/2 of BW. Okay, so this is different than in those tables where we were looking at the minimum thickness of slabs based on span length. This guy is prescribed simply based off of his stem width for a single non-integral T-beam. Okay, so on a quiz or a test or something, if you saw that, that would be one of the questions you would have to ask. Is this beam by itself or is he part of a system? In which case you could make an assumption and then we could verify the assumptions later with the architect as for the layout. So anyway, that's one little subtle difference that we have to kind of consider for for these T-beams. Now, the actual design method is pretty straightforward, and this will look fairly familiar to you if you remember our doubly reinforced methods. Okay, there are a couple of phenomenons that could happen. Again, we're looking to try to establish, the strain diagram. And if you remember back in doubly reinforced, we were looking at, if this is, my T-beam, the location of this neutral axis, where is it at? Does it occur up in the flange or is it down in the web? It's one of those two cases. And so what we're looking at is the first case where the compression zone is fully contained in the slab, or the scenario where our A, remember from Whitney's stress block, is less than or equal to HF. Okay, and when that happens, this is just basically a simply rectangular reinforced section with a BE width assigned to it. And so you can see I've shaded what would be the compression block, and if A is that shaded region is fully contained in here, then I can solve for A just by doing sum of forces X, sum of forces Y. And again, we've gone over all this back in the Whitney stress block, so if you don't recall how that's done, go back and take a look at the doubly reinforced sections or even the singly reinforced SRR beam videos. We've talked about where all that's coming from, but at this point I think you've probably got this down. We've done this several times. Okay, so again, it's the area of steel times Fs all over 0.85 F prime C, and then B, instead of being the width of the rectangular section, is now the width of the flange, so it's this BE value. Okay, and so then ASFY, again, because we're assuming we still want ductile failure, we're going to assume that the tensile steel, which is the steel at the bottom, not in the shaded region, that we want it to yield. So this most often is what we're after, is that he does indeed yield. Okay, so it's basically the same as what you did with the SRR design, except now you're using B equal to the effective flange width that we just saw. Our second case then is the scenario where the depth of that Whitney block, A, drops down into the stem of the web of this beam, okay? And so just like what we did with, doubly reinforced sections and trying to figure out where, or even singly reinforced, where we were trying to figure out, which of these cases controls, it's the same kind of idea that's happening here. And so what we do when we look at analyzing this, again, our effective width is of the flange is this BE characteristic, is that guy. The depth D goes from the top of the beam down to AS, so that's no different. And then A is just simply A is greater than HF is the scenario that we're trying to prescribe here. So the way that we analyze this then is that we basically come back and say, well, let's split these regions up. Okay, because if you look, if I split it into a region that consists of this shaded block, this becomes an SRR beam analysis. And that's what we call the web contribution. And then I can treat the flange portion also as kind of an SRR beam portion. The thing that's different is that this AS, which was the total area of steel in the section, I now have a portion attributed to the flange moment, and then I have another portion, or AS minus ASF, apportioned to what's associated with the web. All right, so once I do that, then I can look at the nominal moment capacity for the total section, or MN, is then the moment that comes from the flange contribution plus the moment that comes from the web contribution. And both of these analyses become kind of singly reinforced analysis. The trick is figuring out how much of the steel is needed to compute the flange contribution, but even that's not real hard. So this is how we start to do it. So let's take a look at the flange contribution. Okay, again, we have our Whitney stress block on this, so we're looking at the first value. So put this back up here. So we're looking at this case here. Okay, and so all I'm going to do is figure out, well, okay, if my A is exactly equal to HF, which is what this scenario is going to say, okay, then my Whitney stress block will look something kind of like the following, and it'll look pretty familiar, right? So the width of the block is limited by the dimension of the flange, so instead of being A, the only difference is now it's HF here. Okay, everything else is exactly the same. The centroid is located at HF over 2. Okay, the intensity of my stress block is 0.85 F prime C. I'm going to calculate C-res for the concrete, just like we did before, and then the moment arm then is D minus HF over 2. Again, all we've done is just basically said A is equal to HF in this picture. Okay, and then everything else is exactly the way that we did it before. Okay, and so when I do that, you can solve for, if C-res is this contribution, the compressive block capacity of the flange, I can then solve for the portion of steel that balances that, doing sum of forces in the x direction. And so that's what's done in this equation here. So ASFY, that's my tensile component. Here's my C-res component. And I basically said those guys are equal to each other. And if I say that ASF is going to yield, then I can come in and I can calculate these portions as well. And that's all we do. So plug in F prime C, BE minus BW, HF divided by FY, and 0.85 is that guy. So that's the flange contribution. Okay, then all you have to do is go in and look at the web contribution. And it's exactly the same way, except now, again, the picture is identical to what we had before, except now the A on this thing, that's A divided by 2. Okay, and so A is the depth of the block. I mean, this is just a pure Whitney block diagram as we learned back with the SRR section when we first studied these. The only difference is that now this guy is no longer just AS. It's the difference, or what's not claimed by, by the flange portion. This guy is now allocated to be part of the web portion. And so I can calculate that web portion times FY. And with that, I can very quickly go in and calculate my nominal moment capacity of AS minus ASF FYD minus AR2. So so the only thing that changed was this piece. Okay, you want to call that as an AS for the web or something, you can do so. Okay, but otherwise everything else of the procedure is exactly the same. So when you do that, then you go back and basically you can solve for the A value, and if you find out that A is less than HF, you know that this is not the case that controls. Okay, if A is greater than HF, then you know that this is the case that controls, and you now have the procedure to be able to start to analyze this. Okay, so it's the same game. Same sum of forces X, calculate your concrete resultant, set it equal to your tensile resultant, and you're off to the races, so to say. So anyway, it's not a real hard concept, so hopefully it makes sense to you. It's basically everything that you've done before. It's just kind of a superposition of different pieces where you're looking at the capacity of what the flange can carry and you're adding it to the capacity of what the web is responsible for, and basically you're making assignments off of that. But the mechanics are exactly the same. They're both just SRR reinforcement sections. You can do doubly reinforced the same way, but now it's a little bit more challenging because now you got to figure out, well, how much of the steel can I count on in the concrete flange for compression, and then, but it's generally the mechanics are exactly the same process. So like I say, like I've done in the previous videos, we've got kind of a worksheet or a flow chart to walk you through. What I've got is a T-beam with certain dimensions and certain center to center span. So watch this, because remember, we need clear span, so I would have to subtract off this web dimension from the center. Most often this is what's called out on a drawing. Okay, we're looking at F prime C of 4,000, FY is 60 KSI, AS is prescribed as some amount of steel. I don't care whether it's number 8s or number 10s or what size the bars are. I just need the total area, because this is the guy that we're going to partition into the flange section and the web section. Okay, I've also given you the simple span length of this beam as being 30 feet. Okay, so basically the basic procedure is you're going to determine the depth. Okay, and again, that comes off of the cover requirements or off of the detail drawings. In this case, I gave you a cover, and I gave you a depth of member. Okay, and then the parameters that you need to compute the effective width are as follows. I need the HF, which is the height of the flange, okay, including the slab. BW is the width of the stem. We have our span length, LU, and then we have our transverse span dimension, clear span dimensions, SU1, SU2. Now, in this case, I only drew one, but what we're going to assume is that this repeats as it goes across. So I think I have 96 inches called out here. So it would assume that 96 to the next one, and so forth. And so you can work on that. Okay, once you do that, then you can calculate the effective width from that simple table. All right, and then we compute the effective width that way, and then with that, I can now go find A and C. Again, you still got to go through all the process of checking your strains and making sure that you put enough strain into that the tensile steel. And we didn't show that check in this exercise, but remember that if my strain diagram is looking something kind of like this, where I'm doing 0.003, and I realize I drew this backwards, but you get the idea that somewhere down here, if my T-beam looks like that, there's my AS, that this guy is my epsilon S, and we want to make sure that in this case, if it's one layer of steel, it's epsilon T, and that needs to be greater than 0.005 in order to be able to get a phi is equal to 0.9. So that's the other check that you have to do. So hidden behind the scenes of all of this is taking our nominal moment and then using that value based on the reinforcing to figure out the strain at this position. Again, this is C, and that we know that C is equal to A over beta 1 is exactly the same process. So you do have to check this strain to make sure that it yields in order to come up with the phi. And then once you get phi, now I can compute the design moment. And that's all there is to it. It's exactly the same as SRR. It's just that one little check with the effective width, and then we have to make those adjustments for the web and the flange contribution. So anyway, hope this has made sense. If you would, leave us some comments down below. Let us know if it's making sense to you, or if there's something that we could do to make things a little bit more clear for you, and to help with the videos in the future. As always, like and subscribe to the channel, and we will see you next time. Have a great afternoon. Happy engineering.